Welcome to Lesson 2.4, Part B. In the first part of this lesson, we examined the graph of a function and used that to determine information about its derivative. Where the function was increasing, the derivative was positive. And where the function was decreasing, the slope and therefore the derivative was negative. And where the function had a relative maximum, the derivative was 0 and changed from positive to negative, from left to right. And where the function had a minimum, the derivative was also 0 and the derivative changed from negative to positive across from that 0. Then we looked at a graph of the derivative and determined the same thing. Similar things about the function. For the second half of this lesson, we're going to look at this analytically. What do we do when we don't have a graph? And this is going to start each time. They ask us to find where is the function increasing, where is the function decreasing, where are the relative extrema, that's the minimums and the maximums. And this is all based on the derivative. So our very first step each time with these types of problems is to find what is our derivative. So my derivative of this function is 3x squared minus 6. Now once I have that derivative, I want to find something called the critical numbers or critical points. Critical numbers. And these are values of x. They will always be x equals. Values of x at which a function has a potential maximum or minimum. A potential maximum or minimum. And if we return to our graphical examples, if I had a function that looked like this, we'd see that it's always where my derivative equals 0 that my function changes from, say, a positive slope to a negative slope, or from a negative slope to a positive slope. It never changes from a positive slope to a negative slope without the derivative first being 0. So finding these critical numbers, these critical points, is going to allow us to essentially break our function up into the intervals that we'll be dealing with. And then the intervals may end at negative infinity and positive infinity on each end. So to find those critical numbers, we saw that they're where the derivative equals 0. So where the derivative equals 0, which means we're going to come back here to our derivative function and set it equal to 0. I want to know where does my derivative equal 0? Then I set my function equal to 0 and solve for x. We can go ahead and solve this for x then. 3x squared equals 6. X squared equals 2. Take the square root of each side. And x equals plus or minus radical 2. Now, with these critical numbers, what we're going to do is set up something called a sign chart. This sign chart helps us find our different values. So my critical numbers are negative radical 2 and positive radical 2. I'm going to list them in order from least to greatest. And what I like to do is immediately then write out what are the intervals that I've defined these as. So this interval is negative infinity until negative radical 2. This interval here is negative radical 2 to radical 2. And this interval is radical 2 until infinity, because there's no other endpoint off on this side. Now I know what my critical points are. I know I have a potential min or max here at negative radical 2. I know I have a potential min or max at positive radical 2. but I don't know whether it's a minimum or a maximum without knowing what's happening to the derivative on either side. Now the great thing is, if I find what the derivative is, whether positive or negative, at any point between negative radical 2 and positive radical 2, let's say that I check it and find that it were positive, then I would know if it's positive here, it must also be positive here, and it must also be positive here, and it must also be positive here, because my derivative can't change signs. I can't go from positive to negative without going through 0. If you think about that, I can't go from positive to negative without going through 0, which means that since I've established that negative radical 2 and positive radical 2 are my only places where the derivative equals 0, then my sign can't change inside the intervals. So I only need to test one value in each interval. So we're going to check what value will I test. Between negative radical 2 and radical 2, an easy one is 0. So we want to find what is the derivative at 0. What is my slope on this interval? So I take this function right here and evaluate that for 0. And it's going to be negative 6. The important part here being that my derivative is negative. Then I want to check a value greater than radical 2. 2 is a simple number, so I'm going to do that one. You could use 3 or 10 or 1,000, but your problems might be a little more complex to solve. I'm going to find the derivative at 2. 3 times 2 squared minus 6 is 6. And even at this point, I can see this will be positive. And then for a value less than negative radical 2, I'll also use negative 2. The derivative at negative 2 equals 3 times negative 2 squared minus 6, which is 3 times 4 minus 6, which is 6 again. So this is also positive. So at this point, I've completed my sign chart, and the really important parts here are where is this positive and negative, and what are the intervals for each of those values. Now I can determine where is my function increasing by checking to see where is my derivative positive. Well, my derivative is positive on negative infinity to negative radical 2 and on radical 2 to infinity, so I can notate that. F of x is increasing on negative infinity, negative radical 2, and radical 2 to infinity. And then looking back in the instructions, I must provide justification of my answers. And just showing the sign chart isn't enough. I need to actually explain what is the foundation for my making the statement about the function increasing. And that foundation is because the derivative is positive. And I can just say greater than 0. Because my derivative is greater than 0. And in fact, from this point on, we'll start with the justification because that helps us identify our answer. So for the second question, how do we know where f of x is decreasing? Well, I know where it's decreasing because f prime of x is negative, is less than 0. Then I look for where is my derivative negative. It's negative here. The function is decreasing. Function is decreasing on negative radical 2 to radical 2. Then it asks us to find the relative extrema. And for the purposes of class and quizzes and tests, always specifically address whether there's a relative maximum and whether there's a relative minimum. If you find that there is no relative maximum, you need to state that there is no relative maximum and why you know that there's no relative maximum. The justifications here are really the key. They're at least half of the credit on a problem like this. So we want to find where do I have a relative maximum. I would have relative maximums where my derivative equals 0 and changes from positive to negative. So where does it change from positive to negative? That would be from here to here. It changes across this critical point. Remember, these critical numbers, those were my values where the derivative equaled 0. So there is a relative maximum at x equals negative radical 2. And then my relative minimum. How do I justify a relative minimum? A relative minimum is where my derivative equals 0 and changes from negative to positive. Minimum looks like this and goes from going down, negative slope, to going up, positive slope or derivative. And my function changes from negative, my derivative changes from negative to positive across positive radical 2. So because f prime equals 0 and changes from negative to positive, there is a relative minimum at x equals positive radical 2. Now, if we look back at the instructions, it doesn't ask us just to state where the extrema are, they ask us to find the coordinates, which means we're going to need to go back to the original function in order to find our y values for those x values. I'm going to copy that down, x cubed minus 6x plus 1. X cubed minus 6x plus 1. So to find the coordinates for each of these, I just need to plug those radicals into my function. F of negative radical 2 is negative radical 2 cubed minus 6 times negative radical 2 plus 1 equals radical 2 times radical 2 is 2 times radical 2 is negative 2 radical 2. Negative 6 times negative radical 2 is plus 6 radical 2 plus 1 combines to 4 radical 2 plus 1. We could find the decimal equivalent, but that gives us our coordinates here, negative radical 2, 4 radical 2 plus 1. To do the same for positive radical 2, positive radical 2 cubed minus 6 times radical 2 plus 1. This would be 2 radical 2 minus 6 radical 2 is negative 4 radical 2 plus 1. Negative 4 radical 2 plus 1. And you can find decimal equivalents, and that would be fine as well. Before we move on, I want to revisit the sign chart and show you a shortcut that you can use if you remember some basics about polynomial sketching in pre-calculus. As you might recall, we first look, when wanting to sketch a function, we look at its end behavior. So for a derivative function, 3x squared minus 6, our end behavior would determine what's happening on the outer ends of our sign chart here. And this is an even exponent of our lead term, which means that, and it's positive, which means that my end behavior is going to rise to the right and rise to the left. So if I were reconstructing my sign chart and all I knew was negative radical 2 and radical 2, I could say that, well, since my derivative is rising to the left, it's going to be positive over here. And since my derivative is rising to the right, it will be positive over here. Then I can look at the negative radical 2 and positive radical 2 and recall that when I solved for them, I had x squared equals 2 and took the square root, and I got positive radical 2, negative radical 2, which means that the multiplicity of each of these roots was 1. I only found each root one time. And when my multiplicity is odd, that means that when graphing my function, or in this case graphing my derivative, that I'm going to, when I hit this 0, go through it instead of bouncing. And then this one has a multiplicity of 1, so I will go through it as well. So now I can tell that my derivative function would have started positive, would have become negative, and then gone back to positive. And that gives me a quicker way to develop my sign chart without having to test the 3 values of the derivative. You are more than welcome to use this method, and we'll use this method most of the time in the future because it saves a lot of time on what's otherwise a time-consuming process of developing the sign chart, and it keeps the sign chart a little bit neater as well. All I would need at this point is my intervals here and here, which is considerably cleaner than this sign chart that I have over here. So we'll go ahead and use this process on the next question. Okay, this is our next function, and the same instructions still apply. We want to find where is my function increasing. F of x is increasing. And our justification. And we want to find where is our function decreasing. And we want to find where does my function have a relative maximum. A relative and where does my function have a relative minimum. All right. And of course, all of these justifications are based on the derivative. So let's go ahead and fill in our justifications, and then we'll find our derivative. I know my function is increasing because my derivative is greater than 0. It's positive. My derivative is positive. My slope is positive. My function is going up. It is increasing. I similarly know that my function is decreasing where my derivative is less than 0, where it's negative, where I have a negative slope. I know my function has a relative maximum because the derivative equals 0 and changes from positive to negative. You do need both parts for the justification because being 0 alone is not sufficient justification for a relative maximum, because the derivative being 0 can also indicate a relative minimum. Our relative minimum, the derivative equals 0 and changes from negative to positive. So we see that all of these justifications are based on the derivative, so we want to go back and find the derivative. The derivative here equals 15x minus to the 4th minus 15x squared. Next, I need to find my critical numbers. Those set off the intervals on my sign chart, and those are going to be where the derivative equals 0. So I solve this for equaling 0. In this case, the first thing I'm going to do is factor. I have a common 15x squared, leaving x squared minus 1 to equal 0. Since I had more than one instance of x that cannot combine, I needed to factor to solve. Now my 0 property says I can set each of these terms equal to 0. I have 15x squared equals 0 and x squared minus 1 equals 0. When I take the square root, we'll divide by 15 and then take the square root. x equals 0. Important to note for our quicker sign chart, this 0 has a multiplicity of 2 because there's 2 of them. 2 roots, 2 x's means 2 roots, so this is a multiplicity of 2. Here I have x squared minus 1 equals 0, so x squared equals 1, and I take the square root and get x equals 1 and x equals negative 1. Each of these occur only once. The 2 roots indicated in this x squared are 1 and negative 1, so they each occur only one time. This allows me to create my sign chart, and my values are negative 1, 0, and 1 in order. And I'm going to go ahead and mark my multiplicities here. This is M2, M1, and M1. That'll allow me to clean this up a little bit here. Now with our sign chart, we can mark our intervals, negative infinity to negative 1, negative 1 to 0, 0 to 1, and 1 to infinity. And now I need to determine where is my derivative positive, where is my derivative negative. Now I can go back to this derivative function in order to see what this derivative would look like, what this derivative function would look like. And again, this is a positive x to the fourth. That's an even power, so it rises to the left and rises to the right. I can mark that here. This will be positive, and this is positive. Then I look at the 0 behavior based on the multiplicities. This is an odd multiplicity, so it's going to start positive and then change. And this is an even multiplicity, so it's going to bounce and stay negative. And then this is an odd multiplicity, so it's going to go through and change, which makes sense. I start with positive, I change and become negative, I stay the same and become negative, stay negative, and then I change and become positive, and I match up with my end behaviors. This allows me to answer then, where is the function increasing? Well, it's increasing where the derivative is positive, and the derivative is positive on these intervals. Negative infinity to negative 1, and 1 to infinity. Where's my derivative? Where's my function decreasing, or my derivative is negative? My derivative is negative here and here. So it is decreasing on negative 1 to 0 and on 0 to 1. And note that I can't just simplify this to negative 1 to 1, because for this brief moment where the derivative equals 0, my derivative is not positive and it's not negative, and my function is increasing or decreasing. The derivative 0 has a horizontal tangent. For a moment it has stopped. So this is my answer. My function has a relative maximum where the derivative equals 0 and changes from positive to negative. Looking back at my sign chart, the only place that I change from positive to negative is across negative 1. So my x-coordinate will be x equals negative 1. And then I need to go back to my original function and find what is my y value there at negative 1. Negative 1 to the 5th, negative 1 to the 3rd gives me negative 3 plus 5 equals 2 for my y value. So at the coordinates negative 1, 2. And my function has a relative minimum where the derivative is 0 and changes from negative to positive. And that happens negative to positive here, which is across x equals 1. At x equals 1. And then I need to find my y value. My function was 3x to the 5th minus 5x to the 3rd. So f of 1 equals 3 times 1 to the 5th minus 5 times x to the 3rd. times 1 to the third, or 3 minus 5 equals negative 2. So my coordinates are at 1, negative 2. And we're done. Much more quickly than the previous time. Our final function is a trig function, and they limit the domain that we're going to check values for to 0 to 2 pi. And we want to find increasing, decreasing, relative maximum, relative minimum. So let's go right in with our derivative of theta is 1 plus 2 cosine theta, and find our critical numbers, or critical points. Set this equal to 0. 2 cosine theta equals negative 1. Cosine theta equals negative 1/2. So theta is going to be any angles that would provide negative 1/2. And looking at our chart here, we find that cosine would be negative in the second and third quadrant. Cosine is negative in these two. It's positive here and positive here. And my reference triangle with 1, 2, cosine is adjacent over hypotenuse, so that would be adjacent to this pi over 3 angle. And we are using the radians, not degrees. So pi over 3 in the second quadrant is going to be pi over 3 less than pi is 2 pi over 3. And in the third quadrant is going to be pi over 3 more than pi, so 4 pi over 3. Now we can set up our sign chart. 2 pi over 3 and 4 pi over 3. Indicate our intervals. Remember, we're given limits from 0 to 2 pi. So my intervals are 0 to 2 pi over 3, 2 pi over 3 to 4 pi over 3, and 4 pi over 3 to 2 pi. Because I was given limits on this function, I can't be guaranteed the end behavior on either side. And really I can't with trig function anyway, because it has that periodic behavior. So I need to go ahead and test points in each section of the sign chart. I want to find my derivative. This was my derivative at, let's say, pi over 3, pi over 3, and find my derivative at pi is between 2 pi over 3 and 4 pi over 3, and say my derivative at 3 pi over 2. That's an easy one to do the chart using the unit circle. And then we can find out, is our derivative positive or negative for each of these values. So at pi over 3, cosine of pi over 3, we said is 1/2, and in the first quadrant is positive. So 1 plus 2 times 1/2. I don't need to solve this all the way out. I can just determine that this is going to be positive. So this portion of my chart is positive. I can go ahead and try each of these others, and we'll do that. But because 2 pi over 3 was a multiplicity of 1, I only had one root of 2 pi over 3. And 4 pi over 3 was a multiplicity of 1. That means that my sign is going to change each time on my derivative. So I can determine now, I can actually see that this would be negative, and changing again would make this positive. But let's test the other values. Pi and 3 pi over 2. Negative 1, 0, and 0, negative 1. So here, f prime of pi be 1 plus 2 times the cosine of pi is negative 1. And so I get 1 plus negative 2 is negative 1, and it's negative, as I expected here. And same thing for 3 pi over 2. 1 plus 2 times cosine at 3 pi over 2 is 0, which gives me 1, which is positive, as we saw here. Now that we have our SLARN chart, we know our critical numbers, and we know where our derivative is positive or negative, we can answer our increasing, decreasing, max and min questions. My function is increasing on 0, 2 pi over 3, and 4 pi over 3 to 2 pi, because my derivative is positive. And because my derivative is negative, my function is decreasing on 2 pi over 3 to 4 pi over 3. Because my derivative equals 0 and changes from positive to negative, the function has a relative maximum. Positive to negative happens across 2 pi over 3. X equals 2 pi over 3. Now we need to find the coordinates, which means the y value also. My original function was theta plus 2 pi theta. F of x equals theta plus 2 pi theta. Sorry, 2 cosine theta. For 2 pi over 3, that'll be 2 pi over 3 plus cosine of 2 pi over 3 we found was negative 1/2. Adjacent over hypotenuse, yes, in the second quadrant. So 2 times negative 1/2. 2's cancel. 2 pi over 3 minus 1 over common denominator. 2 pi minus 1 over 3. So those are my coordinates. 2 pi over 3, 2 pi plus 1 over 3. And finally, because the derivative equals 0 and changes from negative to positive, f of x has a relative minimum at, and I check to see, does my derivative change from negative to positive? It does go from negative to positive across 4 pi over 3. X equals 4 pi over 3. And then I need to find my y value. 4 pi over 3 is 4 pi over 3 plus 2 times cosine of 4 pi over 3 is also negative 1/2 minus 1 times 3 equals 4 pi minus 3 over 3. So my coordinates are 4 pi over 3, comma, 4 pi minus 3 over 3. And I believe up here that this should have been, back here should have been 3. 1 times 3 and 3 here. And that's the end of the lesson. Make sure that you really practice these. They're very straightforward. It's the same process every time. It's just being familiar enough with the process that you can just go right through it without forgetting what your next step is or where you need to look to determine, is the function increasing? Is the function decreasing? Is there a relative minimum? Is there a relative maximum?